Hello, class. Today's lecture will talk about entropy. Now, entropy is kind of a somewhat complex concept, uh, kind of abstract. It's normally defined in a 101 thermo text as being a measure of randomness or disorder in a system, something like that. And that's a pretty good definition, but we'll also describe it mathematically. There's a nice parameterization given in your book that we will take advantage of to be able to explain, I think, in greater detail. So the intent is try to give you even further understanding what entropy is and how it changes and how it responds in different circumstances using monatomic gases, which are relatively simple, as a good starting point. So let's without further ado, let's dive right in. So this is the equation of interest. This is the Sacker-Tetrode equation. And what it basically describes entropy of an ideal gas, in this case, a monatomic ideal gas. And so what you have here is you have S is entropy, and that's equal to all this stuff on the right-hand side, which is the N is the number of particles, K is the Boltzmann constant, and you have a natural log of the volume. This is an SI unit, so it'd be meters cubed. And then you have 4 pi within this 3 halves term here. Mass is your atomic or molecular mass of the gas of interest. U is the internal energy. You have 3 degrees of freedom from a monatomic gas, so it's 3 halves nkt would be your energy here. And that's divided by 3nh squared, and h is your Planck's constant, right? And then you have this extra 5 halves term here. So this is the expression from your text that we will be using to illustrate a few examples. And I'll also give you some Python code at the end to look at that employs this equation and variants of this equation. So let's suppose you have a gas, a monatomic gas like helium that expands into a larger volume. By the way, this is the simplest example. Let's just assume you have a gas, it's in a container, but then it expands that somehow that container expands or expands into a larger volume. That helium expands into a larger volume, but you're not changing the amount of helium. You're keeping the amount of helium constant, so the moles are constant. The temperature is not changing. Maybe you've got some heat input in there that's keeping the temperature constant. So the internal energy is the same. And the question is, what is the entropy change in this very simplified case where we want to keep U and N the same to make a simple problem here, right? But we're not changing the amount of helium. We're not changing its temperature. We're just saying it's now expanding to a larger volume. So what is the entropy change in this simplified scenario? Well, your book doesn't actually derive that for you, so I will do it for you. And what it is here is you have this equation here, right? And one thing we can do to derive that, make it our lives easier is this term here, this 4 pi mu over 3 nh squared to the 3 halves power. These are just constants, right? We remember internal energy is fixed, N is fixed, and these are just constant terms all around. So we can just define a constant C that captures all of that and rewrite the equation like this, in this form. Note, though, that I have written this equation twice, right? So what we're trying to do is get the entropy change from the initial entropy state, S sub I initial, and from the final entropy state. So after the expansion, it'll have an entropy called S sub F. The only difference between S sub I and S sub F is the volume, right? So everything else is the same, because everything else is constant, really, in this case, right? So the only thing that changes the volume. So you have the initial volume V sub I in the S sub I expression, and a V sub final in the S sub F expression. So then you subtract those two to get the delta S, the change in entropy from the initial to final states, which is then done like this. And then, well, we remember our log rules, right? So natural log of A times B in parentheses is just natural log of A plus natural log of B, which is what I've done here. I just broken this up and both of these up in this way. So now you have four terms instead of two inside these brackets. And guess what? You have the natural log of C and minus natural log of C. So those cancel out and you're left with this. And you get a similar thing going with the natural log inverse n terms here that they will cancel out. And so what you're left with is just inside the brackets natural log of v sub final minus natural log of v sub initial within brackets times nk. And finally, you get this final form, right? So this is the Sackur-Tetrode equation for a volume expansion, assuming that U and N are constant or fixed, right? They're fixed. So this is it right here. This is the case. And the Python code that I'll show you later, I'll show you exactly how much the entropy changes for this case, right? Now, now that's the simplest case, the entropy, the volume expansion. Now we'll go to a slightly different case, slightly more complex, not much more so, just a tiny bit more. It's the entropy mixing scenario, where again we have, in this case, we'll imagine you're in a container that's partitioned in two equal halves, right? This half is exactly the same size as the other one, but each half has a different gas. You might have helium in one end, another monatomic gas like argon or whatever in the other end, or nitrogen N or C or something in the other end, right? And then we remove this partition. We just take it away and allow each gas to expand into the expanded volume, right? Mixing with the other gas and increasing entropy. So they both mix into each other and also expand into this new volume. And there's going to be this subsequent entropy change from that, from this volume doubling, right? You've doubled the volume for each gas because you removed this partition and allowed now each gas to go into the second half of the container as well. So now you have, in this case, it's a similar expression to the volume doubling, right? So you have, except, okay, in this case, for instance, for volume doubling, we know that VF over VI has to be 2, right? If you have a tripling, VF over VI is 3. So you can have natural log of 3 if it's a tripling of the volume, or if it's a doubling of a volume, is this term is natural log of 2. Well, we're dealing with a volume doubling here. So this is where this natural log of 2 comes from, because you have V sub f is this ratio V sub f over V sub I has to be 2, 2 over 1 times the nk, right? So gas A, like say if you have gas A on the left half here and gas B on the right half here, and you take away the partition, the change in entropy for gas A uh, over, throughout the expansion, after the expansion, is just nk natural log of 2. Likewise, gas B goes through the exact same process, right? It also expands into the other half where A is and mixes with it. But because it goes to a volume that's twice what it was originally, it also goes through an nk natural log of 2 delta S. So that's how much its entropy changed. So the total entropy change for the entire system is just both of these added together. It's delta SA or delta S sub A plus delta S sub B is delta S total, which is 2nk natural log of 2. So this is the case in which you have, again, gas A in one and gas B in the other. You remove the partition and allow them to expand and interact with each other and mix. And this is the resultant final change in entropy from that case. Right. So this is similar to the volume expansion we talked about before, but not really. Now you have two different gases and they're both adding to the entropy change. So it's like 2nk natural log of the volume change in this case. Now the final case is, let's just ignore the partition. You just have one gas, so that's encompassing this whole, whether it's helium or argon or whatever, you just have 1 mole or whatever amount of gas you have here encompassing this partition. But then let's say let the second gas just be an equal amount of the same gas. So if you have all of this just helium, 1 mole of helium, let's add another whole mole of helium. And in that case, would you expect the entropy to double? No, you would not actually. It would not double in that case. You would expect that, but that's not actually true because if you look at the math of the Sackur-Tetrode equation, for instance, and for for monatomic gas case, you're doubling the amount of stuff within the same volume. The entropy doesn't quite double. You would think that, but let's look at it. So yeah, you would have N would double, right? If you did that. So this is true. That would be consistent with that. But look what happens here. U is 3 halves NKT, and even if you double N here, you've got a double N right there in denominators too. So those N's cancel. But then there's another N here, right? So the N's here don't matter within the parentheses here. But this N does, matters a lot. And it counters and slows down the increase a bit from this doubling of the N. So you have 2N here, 2N there, but they kind of counteract a little bit. So you do get close to a doubling, but not quite because of this 1 over N term. And the reason why you have that 1 over N term, as discussed in your text previously, is that in this case, it's basically assuming that the gas particles are all at the same microstate, so the same internal energy, temperature, and all these other things, modes, and all these characteristics are going to be the same for all these gas particles. So you have, say, n number of gas particles within a gas, but if you divide by n by that same number, then you normalize all that. You're basically saying all the gas particles are the same. They have the same, they're in the same microstate, which is actually reflective of reality of how a real gas works, and allows this equation to satisfy the conservation of energy. It actually turns out if it weren't for this 1 over N term, then you wouldn't be able to satisfy conservation of energy. You get some gibberish. And on that point, so your book has some interesting examples that we're going to actually show with code. So for instance, consider a mole of helium at room temperature and atmospheric pressure. The volume is 0.025 meters cubed. The kinetic energy is 3 halves NKT, or 3,700 joules in this case. So you can plug these numbers into the Sackur-Tetrode equation, and we can calculate the entropy for helium at double the volume, keeping U and N constant. You can mix it with helium with another gas within the same volume, or double helium within the same volume. By the way, this should be a B here. So we're going to look at some Python code and check what all this means, what this looks like. So again, here's some Python code. This is the first case. So we're assuming you have helium within a container, and we are allowing the helium to expand into a doubled volume, but keeping the amount of helium constant and keeping the temperature constant as well, the internal energy constant. And there are 2 ways that you can calculate this. You can use the full form of the Sackur-Tetrode equation, or you can use the simplified shorthand for volume expansion, where you have NK times the natural log VF, or V final over V initial, the final volume over the initial volume, and see what happens. Do you get comparable answers? So I get that the change in entropy from the full Sackur-Tetrode equation in this case for the volume expansion. So we're basically increasing the volume of helium from 0.025 meters cubed to 0.05 meters cubed, right? And so the change in entropy is 5.76. And if you use the other equation, the shorthand equation for the volume expansion, NK natural log of VF over V initial, you also get 5.76. So this is the proof again that the full sacchartetrode and the simplified shorter equation for the volume expansion gives you the exact same answer. And that makes sense because we're keeping U and N constant. If you keep U and N constant in the sacchartetrode equation, it will collapse into this form if you do delta S into the shorter form. But what does 5.76 change in entropy actually mean? Right? So we know the entropy from before the expansion, if you calculate, it's like 126. But then after the expansion, it's 131.7 something. So yeah, this is where this difference is 5.6, 5.7-ish difference between these two numbers. So the entropy change is only like, say, 5% or so. So from a doubling of the volume, keeping U and N constant, it's only a modest change, a modest increase in entropy. So it did increase, it didn't double though, right? Even though you double the volume, you didn't double the entropy. You just increased it like 5% or so. So the entropy increased slightly from doubling the gas volume in this case. Now let's look at the case in where you have helium and argon within the same volume, right? And so you start with helium, like 1 mole of it, and then you add 1 mole of argon, let them mix. What happens to entropy? Well, let's run it and see what happens. So from this run, what we see is that the entropy for helium is 126. That's the same value we got before. But the entropy for argon is a little bit higher. It's 155. And think about that. Why do you think that is? If you said that it's because argon has a higher molecular mass, you would be right, right? That's exactly right. So you actually get more than a doubling of the entropy in this case. When you add an equal amount of heavier gas to helium, the total entropy is 280, which is more than double 126. So the percentage increase in entropy from adding argon to helium is 122%. That's over 100%, more than double because of argon's higher molecular weight. So that's the interesting thing. And now we will have the equivalent case, but instead we're doubling helium with itself within the same volume. So I said before, because of that 1/n term, you don't get, in this case, you don't get a doubling of the entropy. You get something close to it, but it's countered by that 1/n term. So in my case, I calculate that the percentage increase in entropy from doubling He or helium is about 90%, not 100%. If it were a doubling, it'd be 100%, but it's only 90% because the 1/n term inside a natural log makes the entropy increase less than expected. And with that, that's all I have to say about entropy, but I'd be glad if you want to talk into more detail about it. We can discuss it at length. Just talk to me in class, send me an email, and I'll be glad to talk to you more about this. So with that said, thank you very much, and I hope to see you in class very soon.